Okay, so section 9.3 is probably the most fun section in chapter 9. It's all about taking a look at applications in probability, and in particular, we're going to look at a lot of things that have games associated with them in this section. So to start with, we're going to take a look at what odds are. So the definition of odds is that this is the probability, is probability of A is what we've seen before, and probability of the A bar is the probability the event A does not occur. If we talk about odds, the odds in favor of an event are the probability of A compared to the probability of A complement, or we can say the probability of A in ratio with or compared to 1 minus the probability of A. And then the odds against an event are just the reciprocal, just the flip of the fraction. So we have the probability that the not A happens on top compared to the probability that it happens on bottom, or 1 minus the probability of A on top compared to the probability of A on bottom. So, where have you seen odds mentioned or used in real life? Maybe not your real life, but in real life. Do you have one for me?
I don't think it really is helpful. I just thought of maybe odds be ever in your favor.
Hunger Games. Comes up every time. Hunger Games. Okay.
God.
No, you're fine. It always comes up. Hunger Games, they talk about the odds being in your favor, but they're still talking about this. So we're going to get to doing some examples with those kinds of odds here. Do you know of any games where they do this with? Because there are examples. This is gambling stuff, right? What is it? What are the odds of an event, or odds of a game? Can you think of any games that use this?
Blackjack, I guess.
People talk about odds in blackjack, right? So like casino kind of things. Horse racing is one that they always use odds with. The odds of a certain horse winning versus another horse winning. You also see this with gambling that people would describe for like betting on like football and basketball, those kinds of games, when people gamble with those kinds of games. Odds is used in gambling. Here's the deal. We've actually done it, and you just didn't know it before. Odds is actually just a part-to-part comparison. Do you remember we did part to whole and part to part? Okay, jot yourself down a note. Probability is part to whole. Odds is part to part. Now, that doesn't exactly explain everything about it, but it is the difference between the two. And people use these two things incorrectly all the time. They'll say odds when they mean probability, and they'll say probability when they mean odds. Okay? So when we talk about, right, like the probability that it will rain today, that's what they show on your weather app in your phone. The probability. That's not odds. But people still use the word incorrectly and call it odds all the time. So what it really is when we're looking at odds is you're looking at the likelihood that something will happen compared to it not happening. Whereas probability compares the likelihood that it will happen to anything happening, right? Any outcome, including the one you want. That's the difference. So when we take a look at this example, this is a really simple one. We've got 8 marbles. 5 are red, 3 are white. Everybody got what we picture. Give me a picture of this? Okay, we could draw a picture if we wanted to, right? 5 red, 3 white. We want to know the probability that we will choose a red. So this is stuff from the previous section. What is the probability of choosing red? Yeah, so there's 5 red marbles and there's 8 marbles total. This is a 5 out of 8 probability. Okay? Now, if we want the odds of choosing red, we still have the same numerator. It's still red on top. There are 5. But on bottom, instead of comparing it to the entire number of marbles, we compare it to the marbles that are not red. In this case, that's only white marbles. But how many marbles are not red? 3. So the probability is 5 to 8, but the odds are 5 to 3. Okay, it's the comparison. What are we comparing things to? Some of you are still working on redos. This happens in your last example, number 3. You have to be 13, excuse me. You have to be really careful when you're looking at that one. Like, what are they comparing? Is it men to women or women to men? And it matters in that problem, right? What are we comparing? Are we comparing the red marbles to all the marbles, or the red marbles to the marbles that are not red? That's the difference. So taking a look then further, let's do my rain example. So if we have, the probability of it raining is 60% or 0.6, right? If we write that as a decimal. What are the odds? And then you have to be careful. This one now says against it raining. Odds against. Well, the odds against it raining mean that we're looking for the probability that it does not rain compared to the probability that it rains. Okay, that's like odds against. It has the opposite effect on top of what you could be comparing it to, right? The probability it does not rain compared to the probability it does. Well, what's the probability, or in this case we could look at percent chance that it does not rain? That's 40. You can even write 40% in if you'd like. And what is the percent probability, or probability in percent form, that it does rain? 60. Okay, and then we would reduce this. So the percents cancel. That's fine. What is 40 divided by 60? Well, you might say, well, that's the same as 4 over 6. We can reduce it one more time. What would that give me? 2 over 3. We have a 2 to 3 odds that it will rain. 2 to 3. Now, obviously, because we've done two of these problems where we've kind of moved in and out of probabilities and odds, there's clearly a relationship between the two, right? They're related quantities. They're not the same quantities, but they are related quantities. So here's a formula, kind of, or an expression that shows the relationship. If the odds in favor of an event are m to n, so this could also be written m over n, right? Then the probability of the event is m compared to m plus n. Right, the probability is the event that we're comparing it against and the event itself, m and n. And if you want the odds against the event, then you want the number of ways that the event doesn't happen, which would have been the denominator of the original odds. So that's the n that's on top, again, compared to either of those options happening, m plus n. All right, so let's look at an example. We're going to do a 3-child family. So we've done some of these tree diagrams. We're going to do one now. So we're considering a 3-child family, and part A is going to ask us the odds of having all of the children the same gender. So we're going to start by doing child number 1, and child number 1 is either a boy or a girl. Okay. And then we have child number 2, and they're either a boy or a girl. Boy or girl. And we can do child number 3. And they're all boy, girl. Oh, I got them all. You can put 1/2 along all the branches. That's fine. Because these are all equally likely branches, we can also just count the answers at the end. If you didn't want to do a tree diagram here, you could avoid it. You could just make sure you have a detailed listing of all the options. And you can see them coming about from the tree diagram if you see them as well. Option number 1 is boy, boy, boy. Option number 2 would be boy, boy, girl. Option number 3 is boy, girl, boy. Option number 4 is boy, girl, girl. Right? So if you were being strategic and careful and listing all these out instead of writing a tree diagram, that would be another way of doing this problem and avoiding the tree diagram if you'd like, because they're equally likely. So this is like my example where I was pulling the numbers out of the hat 2 at a time, right? Where I had another way of doing it and writing them all out. So there's all these different options. I'm not going to write the other 4, but I think you have the idea. This wants to know the odds of having all the same gender of children. In other words, all girls or all boys. So what we want is the number of ways that we get all G's or B's, right? All boys or girls, compared to the number of ways that we don't get this. Okay, so looking at the diagram or looking at your listing, if you've listed them out instead, how many options give us all boys or all girls at the end? 2. And they're the top and the bottom branch, the way that we've drawn them, here and here. There are two ways. We either get all boys or all girls. How many options don't include those? There are 6, yeah. So you can count the remaining branches up. There are 6 of those. And if we reduce, this is a 1 to 3. So you have a 1 to 3 odds of getting all the same gender of children. You have a 1 to 4 probability, by the way. It's not going to be the same thing. It's a 1 to 4. This is a 1 to 3. Then when it says what are the odds against, we don't have to reconfigure this. Like, we don't have to find it all again. All we have to do over here when we're finding odds against is count them again from our diagram. So the top is the number of ways that we don't get all of these. Sorry, that's not the screen that I wanted. Which one was it? This one. Okay, so this probability, this is the number of ways we don't get what we want on top compared to the number of ways we get what we wanted on bottom. It's the opposite. And in particular, I mentioned when I showed you this that we're flipping the fraction upside down, right? If odds 4, we flip it upside down, we get odds against. So if the odds in favor of this happening are 1 to 3, then the odds against it happening would be 3 to 1. And you can't just write that this equals 3. It has to be written as a ratio. And if it bothers you to write it as a fraction ratio, feel free to use the colon notation. 3 to 1 like that. Okay, it does feel a little bit weird, I know. But you have a 3 to 1 odds against having all the same gender of children. Okay, so one of the applications in this section is odds. We're about to shift gears to the other application in this section. You ready? Second application in this section is called expected value. So if the possible outcomes for an experiment are A1, A2, A3, all the way up to AN, with corresponding probabilities P1, P2, P3, all the way up to Pn, then the expected value is the sum of the products of these quantities. So I multiply expected outcome A1 times its probability, P1, outcome A2 by probability P2, all the way to outcome AN by probability Pn. And a game is considered to be fair if when I multiply out all of that and add it all up, I get 0. That is a fair game. So we're going to do an example with a game. It may not be a game you're familiar with. Have you seen a roulette wheel before? Looks like a big giant spinner. It actually includes numbers from 00 up to 36. Okay, so there's a 00, and there's a 0, and then there's a 1, 2, 3, 4, all the way up to 36. Okay, that's how their numbers work. One way you can bet is to bet on a single number. So you can say, I want to bet all my chips on the number 5. It's my lucky number, I like the number 5. That's not my lucky number. I don't have a lucky number. I bet, whatever. You know, this is how people talk, right? I really like this number. I'm going to put them all on this number. This is not the only way to bet, but we're going to examine this particular one. So if the ball then lands on your number, so what it is there's a ball spinning around while the wheel spins around, and then everything comes to a stop eventually, and when they look at where the ball lands on the wheel. That's the way this works. If the ball lands on your number, then you receive 35 chips plus the one you bet. So the payout's huge, right? So like if you bet $10, then you're going to get back 35 $10 bills. It's a lot of money. Plus your original $10 you bet. Everybody with me on how that works in the payout? Okay. So we're going to figure out first, what is the probability you will land on 0, and then what is the probability you will land on 0, right? The ball, not you, the ball. So what is the probability that the ball lands on the 00 slide? Or slot. Well, there's one 00 slot, right? How many slots are there total? There are 36. Okay, does that make sense? Oh, there's not 36. Take it back. 38. That's the word I wanted. 38. There's 36 plus the 0 and the double 0. So 36 that are numbered from 1 to 36, and then there's 2 more. Okay, so there's 38. So what's the probability that it lands on 0? This is not a trick question. Still 1 out of 38. You bet. Okay, everybody with me? So the ball rolls around. It's a 1 out of 38 chance it lands in this one space, another 1 out of 38 chance it lands in this other space. Okay, so this is a true story. My father-in-law is not very good at math. He's a fantastic person. He's really good at building things, and he makes a lot of money by building, but he is not good with math. So he and my mother-in-law go on a lot of cruises, and they just have a lot of fun with the resources that the Lord has given them. And they're not addicts. I don't want you to think he's a gambling addict or anything like that. But if you've ever been on a cruise ship, you can walk through the casino. Usually it's a shortcut to get somewhere else. This is the way it works. And they catch you that way. And so my father-in-law will notice the roulette wheel, and they've got like a screen, kind of imagine like a projector screen next to the roulette wheel, and you can see what it's done recently. Look, it landed on 5, and then it landed on 14, and then it landed on 0, and then it landed on 22. You can see the history of the roulette wheel. Everybody good so far? Okay. So when my father-in-law goes through the casino, he looks at the history of what it's landed. And if he does not see that it has landed on the double 0 or the 0 on the board, he'll bet. These are independent spins, right? One spin has absolutely nothing to do with the other spin. Everybody with me on why this doesn't make sense? Okay? This is what he will do. And so he will bet on that spin, that the next spin is going to land on 0 or double 0. Okay? So then he puts a chip on each one of those numbers. That's what he'll do. He'll put one chip on the 0s, and he'll put one chip on the double 0. Okay? Everybody good? Okay. Well, there's I shouldn't say it that way. There's 2 possible outcomes. There is the possibility that he wins, and then there's the probability that he wins. So let me say it this way, actually. Let me write down what I have. So we're finding expected value. The expected value is that the value of the win times the probability that he wins. And then we have the value that he loses, like this is actual numerical value, like money. The value of the loss, or that he loses, compared to the probability that he loses, so the probability of loss. Okay, it's either or. It's not one or he's either going to win or he's going to lose. Agreed? If they either give him money or he leaves and he's spent his 2 chips and he's out the money. Those are the only options. Now, if a single chip is worth $10 and he's betting it, and he loses, what does he lose? $20, because he put a $10 chip on the 0 and he put a $10 chip on the double 0. Is everybody tracking with me? Okay, so I'm starting with the easier answer. So this one over here, the value of the loss is he loses $20. That's what happens if he loses. How likely is he to lose? Well, maybe let's answer how likely he is to win. We're kind of bouncing around. There's 4 things we're going to figure out, right? These 4 pieces. How likely is he going to win? Well, it's a 1 out of 38 chance that it lands on 0, and it's a 1 out of 38 chance that it lands on double 0. So what's the probability that it lands on one of them or the other one? 2 out of 38, right? It's 1 out of 38 for one, 1 out of 38 for the other. So there is a 2 out of 38 chance that he wins. So what's the chance he loses? There's 36 options of ways that he loses out of 38. Does that make sense? Okay, these are the 3 values that are pretty directly, like you can see where they're coming from the picture we've already described. Everybody good so far? Okay, let's figure out what the value is if he wins. Okay, so if he wins, it says he gets 35 chips. 35 chips, $10 each. How much money is that? $350, thank you so much. $350, right? He gets the $350, but they also give him back the chips that he originally had for one of them. because it's only going to land on one of them, right? So he's going to get back, so he's going to have 350, and he's going to get back the one he originally spent, but that's not money he's gained, right? That's the money he already spent on the one, and one of them he's still going to lose. Are you with me? Okay, so like let's say it lands on 0. Well, then the chip that he put on the double 0, the dealer takes that chip away. He gives him back the one that he put on the 0, and he gives him 35 more. Okay? So in his pocket now he has 35 plus the one he had originally. So it's 35 of benefit, but he had one taken away. He's got 34 difference, right? He's got 34 more than he started with. He originally had 2. Now he's got 36. He has 34 more than he started with. So the value is not 350. It's actually going to be 340 because he still lost one chip. Okay, the one that he got back just means that he didn't win or lose anything with that particular chip. Like it's refunded. You know, it's your refund, right? Like that's what happens when you send stuff back to Amazon. They just refund your money. It's like you never lost it, right? Okay, and we're going to calculate this. We're going to use your calculator. So you're going to take 340 times 2 over 38 plus, notice this is a negative. It matters that it's a negative 20 plus 36 out of 38. This is a dollar amount, so we need to round to 2 decimals because it's got to make sense in terms of money. Does anybody have a amount yet? Okay, did everybody get a negative? You should be getting a negative. Negative 1.05. Okay. So on any given bet that he makes, his average loss is going to be $1. It's about $1, right? Let's just say $1 so that we can talk about it that way. He's going to lose about $1. Every time he does this scenario, he's going to lose about $1. Now, he's not really ever losing $1, right? He's either losing 20 or he's gaining 340. I mean, those are the two options. But this is what would happen. Remember Bernoulli's law of large numbers? If he did this a whole bunch of times, right? If he did this 500 times, 700 times, on average, he would lose $1 every time he did it. Does that make sense? This is a large number average situation, not an individual situation. Okay? He doesn't large number do this. He spends and does it one time, then he's out of there. So he's never going to lose, this much money. But he probably loses $20 most of the time if he does it with these numbers, right? Probably. Okay? As a caveat, my father-in-law is a pretty lucky guy, so this doesn't work out. I don't really know why that is. Why does it seem that there are some people who are just lucky? Do you know people like that? I have a nephew who's really lucky too. He always gets the claw thing to work, gets called up on stage in concerts. It's crazy. Just luck. All right, let's do another one. Deal or no deal. Have you seen this game before? If you haven't seen it on TV, it's in a lot of the arcades now. Chuck E. Cheese has one. Even so, Dave & Buster's, those kind of arcades will have these. Deal or no deal. In this show, Deal or No Deal, a contestant chooses a case. And in our scenario here, they're down to 2 cases. So one case is theirs and one case belongs to the bank. One case has $250,000 in it and the other case has 10. It happens like this a lot too, where the two numbers are very far apart, by the way. If you're the banker and you want to give a reasonable offer to the contestant, but not too lucrative, so too lucrative means it's too beneficial to the contestant, what deal would you offer and why? Well, you want it to be about the average of the 2 cases, right? So here's our option. This is another expected value situation. We want it to have, one option is that they win $250,000. And there's a probability here. And then the other option is that they win $10, right? Their case has one of the 2. What's the probability that their case is the $250,000 case? What is it? It's 1/2, right? There's one case that has $250,000 and one that doesn't. This is 1/2. These aren't odds, these are probabilities. What's the likelihood that their case has $10 in it? It's the other 1/2, right? So go ahead, let's figure out what this is. What happens when you multiply these and add them together? This will be our last question. Did anybody get a value yet? $125,000. What was it, Jaden? And 5. Yeah, $120,005. This is what you get. So what you would do if you were the banker making the decision to make an offer is you'd offer them around this number. It's got to be pretty close to this number for it to make sense. So you're the banker in this situation. So you'd offer approximately $125,000. It says, and why? And the reason is because $125,000 is the average, $120,005 anyway, is the expected value. Slightly more offered is better for the contestant. Slightly less is better for the bank. Does that make sense? Now, this isn't a fair offer. Fair means expected value 0, right? This is supposed to be an adequate or an expected offer that makes sense. It's a reasonable offer. Okay, it's a reasonable offer. So the word fair actually has a mathematical connotation here that we're not using on purpose. Okay, we're talking about it being reasonable. And we'll stop there for today.